So today we will start discussing the approaches for nonlinear modeling of reinforced concrete structures. And before we discuss that, actually there should be a detailed topic about nonlinear behavior of structures, right? Nonlinear behavior. But I'll just skip that one. I assume that you will go through the already available video lectures on nonlinear behavior of structures, because first there is a nonlinear behavior and then we model that behavior, right? So modeling is after we understand the nonlinear behavior. All the possible nonlinear modes of failure, we must first understand those failure and then we try to simulate or model them in a computer program. But I'll skip that first part, behavior part. Please go through the available lectures, and I'll focus now on the nonlinear modeling of structures, and how we can try to account for different aspects of inelasticity in our computer models, right? So nonlinearity can be of two types: material nonlinearity and geometric nonlinearity. There are other types also, like boundary conditions nonlinearity or contact nonlinearity, but mainly there are two broad categories. The word nonlinearity simply means that the behavior is between any action and corresponding deformation is no more linear now, which means that the deformation is no more increasing in the same proportion with applied action, right? So when it is no more increasing or decreasing with the same proportion or with a linear relationship, we call it as a nonlinear behavior, right? So there are well established reasons for material nonlinearity. For example, why different materials deviate from the linear action versus deformation relationship after a certain level of action or applied forces, for example. So we will discuss basic approaches how to account for those nonlinear effects in our computer model. So the aim of nonlinear analysis is to simulate all significant modes of deformation and deterioration in the structure from onset of damage to complete collapse. So a nonlinear analysis should be able to capture or predict the damage or any significant mode of failure or deterioration. So the model should have the capability to capture that failure. If it is based on a linear relationship F is equal to KU, it will never be able to predict that failure, because it will keep on increasing deformations with increasing applied forces. So therefore a nonlinear model should be able to capture all local inelastic phenomena, for example concrete cracking, crushing, yielding, and some other buckling, bond slip. All those are nonlinear phenomena, inelastic phenomena, right? And a nonlinear model should be able to capture them. There should be a feature in that model which take care of these material deterioration. So there can be several nonlinear modeling approaches. Some are very detailed, some are approximate, because our ultimate goal is to capture all these things. So there can be very detailed approaches to capture them, and there can be some simplified approaches also. So here this figure is taken from ATC 72. Please check that reference. Very useful guideline about nonlinear modeling of RC structures, right? ATC 72 report is available. I think you can check that. So here on the left hand side you can see one column which is subjected to the cycles of applied loading and unloading and reverse loading in the opposite direction. So it's like it is applied this kind of a loading, unloading, reloading, and it had several of the non-linear effects in it, concrete cracking, it can have rebar buckling or shear failure or any other failure. Now on one extreme we have what we call as continuum models. Continuum models are very detailed models which try to simulate the physics of underlying physics of that structural element, right? So you will discretize your structure with very small elements, and whatever nonlinear effect is expected, it is expected that this model will be able to capture. This is called physical you can say type of model, in which we use continuum elements or continuum approach to model a particular element, and all those nonlinear effects are expected to be captured using this approach. So if there is a crack, those elements which will be overstressed and will result in cracking, they will be visible being overstressed in this particular type of model. Then there can be, on the other extreme, there can be phenomenological models, and one example is the concentrated hinge model. Concentrated hinge model says that instead of discretizing our whole element into very small elements, finite elements, and instead of simulating the inelastic effect right at the most fundamental level, why not we kind of lump the nonlinear action only at certain locations, and in between those locations we assume a linear elastic behavior. Obviously this kind of a model will not be computationally very expensive or very demanding, but on the left hand side you have continuum model which can be very computationally demanding, and sometimes continuum model may not be developed for the whole RC structure. It may be developed only for one element, right? But this concentrated hinge model offers the simplicity and the ease in the modeling, so that it can be applied for whole structure, right? The basic idea is that nonlinear action can be assumed to lump only at certain locations where we expect the most effect of nonlinearity, right? We assume that only at that point is the inelastic action, cracking, yielding, everything, and in between these 2 points we assume a linear behavior. So whatever is the net effect of inelasticity, we lump it at certain locations, right? So it's not that we are assuming that only there is a nonlinear action possible at ends. It is like we are kind of assuming that all action is lumped at this location, right? So whatever is the total effect of cracking, that effect we will account only by introducing 2 additional elements or few additional elements, hypothetical elements in our model, and those additional elements will take care of or will account for that inelastic effect. So instead of simulating the actual physics of that inelastic action, we lump that action, right? We assume that the total effect we try to estimate, and we lump that total effect and put it in the model, so that model can know and account for that effect, right? In between these 2 extremes is another approach called distributed inelasticity approach, or one of the examples of distributed inelasticity is called fiber modeling approach, and as the name indicates, that it is in between, that you lump the nonlinear action at certain locations or you distribute it along the length, right? So it is also not very simple like the concentrated hinge, and not very detailed like the continuum or detailed micro models, right? So they are in between. So the inelastic action is assumed to be distributed along some length of the element. It can be the whole length or it can be some part of the length in which the inelastic action is the most, right? So based on the main concept of how we account for nonlinear action, there can be three types of nonlinear models, right? Obviously these two are the most suitable for structural engineering applications. The first one is only suitable for detailed evaluation of only one particular or few particular elements, right? For full structure, you should either go for concentrated hinge approach or distributed plasticity approach, right? Sometimes it is called concentrated plasticity and distributed plasticity, right? So let's have a quick discussion about three of these approaches. Continuum models explicitly model the nonlinear behavior. They try to model the behavior at the most fundamental level, right? They are not trying to lump something and account implicitly something. This is an explicit model. So whatever is the real geometry of that element, you will model with very small elements, and each element will be given a realistic material behavior. So whatever is the material disintegration, cracking, yielding, it is expected to capture that behavior because it is composed of all those small elements. So if there is a steel bar embedded in concrete, this particular model will have thousands of small elements. Some elements will be given a steel stress strain behavior, those will be representing a steel bar, and other elements will be representing concrete elements, right? Concrete around that steel bar. So there can be finite elements which represent concrete, longitudinal steel, shear steel. Everything can be explicitly modeled, right? So the real material is modeled and the real material behavior is given to all those elements. But obviously this is a very detailed model, and it is trying to simulate the underlying physics of the material and element. So no predefined behavioral modes are enforced. Like we do not tell the model that the relationship between a particular action and deformation, like moment and curvature, moment and rotation, should be this one. We do not enforce any behavior, any action versus deformation. We define material, and whatever is the nonlinear action, it automatically manifests from that material behavior, right? So they do not require definition of member stiffness. They directly start at the material level. So no need to directly define member properties or cross-section properties, right? So all those properties which are in hierarchy above from material level, like cross-section level, member level, structure level, they are inherently captured in the model through those material properties, right? So it's like putting the nonlinear behavior right at the start of the structural analysis process, at the base of that process, and that is material property, right? Lumped inelasticity model, the other extreme, or concentrated plasticity model or plastic hinge approach, it assumes that the nonlinear action is lumped at certain locations in the structure. The whole structure is not nonlinear. Each point in the structure is not nonlinear. Only few points can exhibit nonlinear behavior, and the overall nonlinear effect is lumped at those points, right? So we directly define the nonlinear action versus deformation behavior at those points only, right? The actual deformation may be distributed along the length of the element, the actual nonlinear deformation, but we assume that the whole effect of that nonlinear deformation is lumped at a certain location only. So that model is simple also, but at the same time the overall inelastic effect can be captured, right? So in these kind of models, you may not be able to see a crack which is traveling in a particular element. You may not be able to see that, when the load is being applied. But in the continuum models, you will be actually able to see that. You apply load and you will see that some of those small elements will be highly stressed, and that is showing cracking. So you will be able to model the propagation of damage also if you use the continuum model. But here in lumped approach, you cannot account for the local level failure like cracking and all that explicitly. You implicitly account that using some hypothetical elements only located at certain locations, right? So that effect is implicitly accounted. So the nonlinear functions between actions and corresponding deformations are assigned at those points. So those points are in our control. If there is a beam, I can select 2 or 3 points in that beam, and I say that now I will control the moment versus rotation behavior at these 3 points or 2 points, right? So I'll give my own behavior input in the program, and the program will follow that behavior. I can define that at this particular point the beam's yield capacity is this much. If the applied loading is causing a moment more than this number, the beam will actually yield in real. So the model should be able to tell that this beam has yielded. So that beam capacity or every input I have to define at that point. So we define nonlinear functions between actions and deformations. This word action versus deformation will come again and again in this whole discussion. Action versus deformation, I will explain it in next few slides, but let me just quickly highlight here that there can be several actions, structural actions in a particular frame element. For example, any 3-dimensional frame element can have 6 actions, 2 moments, 2 bending moments in about 2 cross-sectional axes, 2 shear forces about 2 cross-sectional axes, 1 axial force and 1 torsion. Actually they are corresponding to the 6 degrees of freedom, 3 rotation, 3 translations. So each of those actions have a deformation. Torque have a twist, axial load have an axial shortening or elongation depending upon the direction of axial load. Moment have rotation, right? Moment shear have shear deformation. So every action have a deformation, and in a linear elastic model by default the relationship between action and deformation is by default linear forever. You can have even closed form expressions like for example, let's take the example of torque and twist. You know that you have seen this formula TL over JG. This is theta. For any applied torque to a shaft T having a length L, the theta which it will produce is torque angle which it will produce is this one. Similarly, axial load P and axial deformation delta, it have a linear relationship because you know that delta over L is strain, right? And you multiply capital E with it, right? And this will become sigma. Sigma is equal to P over A. So delta will become simply PL over AE, right? So delta will be, let me write here, delta is equal to PL over AE. So each action can be related to its deformation through a constant quantity called stiffness, right? So F is equal to KU Hooke's law is not only for one full structure, it is not only for one spring, it is applicable for all actions also. Any action and deformation can be related by a simple equation in which there will be a constant. The form of the equation will be simply same as Hooke's law, that action is equal to some constant into deformation, right? Or deformation is equal to 1 over constant into action. So by default, all the actions and deformations, the relationship between them is linear elastic as defined by Hooke's law forever, right? But we change that action deformation relationship when we define a concentrated hinge at a particular location. We define our own relationship which is different from this. For example, now this is a linear relationship. Let's assume that I have a cantilever like this, a bar, right? And some P is applied like in this direction, right? So if this bar is linear, it will follow this behavior forever. But we know that after some loading P, after some level, this bar will yield if it is a metallic bar, right? So what I will do if I want to make a nonlinear model, that I will select one particular element, point, and at that point I will define my own relationship between P and delta. That will be different from this linear relation. Let's say that original linear relationship was this. So what I will do to account nonlinearity in this model, I will change that relationship to a nonlinear relationship after a certain P value. Let's say this is P corresponding to the yielding of that bar, right? So I must know that at what force this bar will yield, right? So that I can start deviating the line from that point onwards, and then what will be the post yield behavior of this bar. If it is a metallic bar, then I may use a bilinear kind of a deformation, force deformation behavior, right? And in more sophisticated nonlinear model, I must also be able to define a cyclic behavior for this bar at that particular location which I selected as the location of lumped inelasticity, right? So I must be able to define the cyclic P versus delta relationship, that if the applied loading is such that it is giving it this bar cycles of loading, unloading, reloading, what should be the behavior of this bar. So this curve which I give as an input now starts governing the behavior of this bar in a nonlinear model, right? So we can do this for any action and deformation. If there is a beam, we know that the primary action is bending. So we can define at certain locations a nonlinear behavior between bending moment and the corresponding deformation, which is rotation of the beam. Right? So beam bends, and when we take tangent at any deflected shape, the horizontal angle of that tangent is the rotation. So the more bending moment is applied, the more beam bends and there is more rotation. So we can directly put our own moment versus rotation behavior at certain locations in our beams, so that we tell the program that this is the moment at which beam will yield and how this will behave after yielding, depending upon how the line is behaving. So one example is this concentrated hinge element. I mean, how we include that nonlinear action deformation behavior in our computer model. We introduce few hypothetical elements in our original structural element at certain locations where we want that nonlinear behavior, and those elements they just take one curve as an input, one action deformation nonlinear curve as an input. So for this bar example, since the axial loading was our main concern, so I can define at one particular critical location, I can include one hypothetical point or element in my model, and give that element this P delta nonlinear relationship, or maybe cyclic nonlinear relationship, as an input to that point. That hypothetical point element is called hinge element, right? So and concentrated hinge element actually, because this is concentrated at a particular point. So sometimes it is also referred to as the zero length hinge element, because it is a hypothetical element which doesn't have any length. It is a point element, and its purpose is to just tell the program that at this location the nonlinear action is lumped and the nonlinear behavior is governed by the action deformation curve given to this particular element, right? Actually, I'll discuss that in more detail in next few sessions. But in nonlinear modeling, this is the main question: from where we will first get the complete nonlinear force deformation curve of our action and deformation, right? So there are several ways we can get these curves. One is from experiment, one is from analysis, that you perform nonlinear analysis at element level and develop that relationship and give it in the computer model as an input. And then there are several international guidelines and documents which guide us about these nonlinear action deformation behaviors, right? So there are several sources from where we get this information, but this is the key information in nonlinear modeling. Like including a hinge element at a particular location, inclusion, that is just one step process, that is simply a practical thing to do. The main issue in the nonlinear modeling is to get the accurate nonlinear curve which your structure or component is expected to follow under the loading, right? If that is accurate, then your whole computer model will behave in a more accurate manner. Any error at this level will include a wrong nonlinear behavior in your computer model, right? So this is one important aspect which we will keep on addressing in next sessions also. But just imagine for now that you have that relationship, and if that is available, you define a hinge at a location and assign that hinge this relationship, give this as an input to that hinge. Hinge have only one input, and that is a nonlinear action deformation behavior, right? It has no length, it has no dimensions, anything. It just gives that relationship in it, and it force the analysis to follow that relationship, right? So during the analysis, during the earthquake is being applied, any particular time instant, the moment increase from the yield moment defined by that hinge, or the axial load increase from the axial yield capacity defined by the axial hinge, the program will tell directly that this element has yielded, this is damaged, right? So by now you must have guessed already that there can be several types of hinges now, depending upon what action and deformation behavior is given to a hinge. So this particular bar example at the bottom right, the hinge will be of axial type, because it will be having an axial force versus axial deformation nonlinear curve as an input. But for a beam, if let's say we have a beam and I select 2 points, 2 corners of that beam to be the location of lumped in elasticity, then the primary action for beam is moment. So these hinges should be of moment type, moment versus rotation type, right? So these are, bottom one are axial deformation hinges, these are flexural hinges at both ends. There can be a shear hinge also. At a particular location, I can, for example, this midpoint, I can say that the shear force at this location, if it increase from the given capacity which I give, program should be able to tell me So what I will do, I will define a shear hinge at that location, and that shear hinge will require a nonlinear relationship between shear force and shear deformation. So that program will monitor the demand shear force at that point, and if it increase from the yield shear capacity which I give in the form of that curve, the program should be able to tell after the analysis that this beam has failed in shear. These things were not possible in linear model. Just imagine shear failure occurring as a result of some applied loading was not automatically predicted in linear model. It will simply report the bending moment and shear force diagram. Whether the actual beam will be able to sustain that bending moment or shear force, that model was not able to tell, but this nonlinear model will be able to tell, right? Because it have certain points in it in which we force it to follow a nonlinear behavior, right? So there can be a other type of hinges also: shear hinge, moment hinge, axial hinge, and some other types also. So these hinges in lumped inelasticity models, they lump the nonlinear behavior. Any behavior can be flexural, can be shear, and that behavior is defined by a nonlinear function. In case of flexure, it is end moment and resulting curvature or rotation. Sometimes we use a moment versus curvature hinge, sometimes we can use a moment versus rotation hinge, right? So action and deformation relationship is used. This nonlinear function should correspond to the observed force deformation behavior and hysteretic test data of similar beam or column components, right? So this behavior nonlinear relationship we get from sometimes experiments, extensive experimentation. Sometimes we use guidelines from different international codes and standards. So but the summary is that they should correspond to the real behavior, right? So there are several tests which are currently being performed on different structural components, and most of them structural level tests, they involve the application of lateral load and then reversing it in the opposite direction and keep on applying cycles, and at the end those results report the action deformation behavior in the cyclic experimental behavior in the cyclic manner. So those experimental results, they are used, they guide us that what input parameters we should use for our nonlinear model, right? So for any, let's say, beam or axial load, whatever is the action, like moment and rotation, like stress and strain, like axial load, axial shortening or elongation, torque, twist, shear force, shear deformation, whatever is the action, it is applied in a cyclic manner, and at the end of that test we get the cyclic behavior, and that behavior guide us about what input we should use in the numerical model of those similar components, right? So we cannot test each component of our building in lab, so we rely on the existing experimentation and international guidelines and other resources, right? But the idea is that our nonlinear model will be only as accurate as the accuracy of these relationships, right? So I'll tell you in next few sessions that from your practical application of nonlinear modeling, from where you should get these relationships, right? Distributed inelasticity is in between, right? That you distribute the inelastic action at certain length, right? So no need to lump only at a certain location, no need to make whole structure nonlinear using small discretized elements, somewhere in between, right? So they can explicitly capture some aspects, but others can be implicitly captured, right? So you may be able to trace the progression of structural damage in this kind of a model, but then very localized kind of failure, you may not be able to handle that explicitly. For that you may be using some implicit relationship, right? So they are somewhere in between the detailed continuum models and the simplified concentrated plasticity models. They are in between. For example, the complete nonlinear stress strain curve of material can be defined to capture important aspects of material nonlinearity. So material cracking, crushing, yielding can be explicitly accounted in these kind of model. But the integration of flexural stresses and strains, the cross-section level stress resultants, they can be implicitly accounted in this kind of approach. So they are based on some behavioral assumptions like plane section remain plane in combination with explicit modeling of uniaxial material response. So the basic idea in these models is that you still define a nonlinear stress strain material stress strain curve for your material, just like the continuum models, but you do not discretize your full structure into very small three-dimensional elements. You use some simplified elements, sometimes called fiber elements, to define nonlinear material behavior in your computer model, right? And those fibers can continue along the whole length of the element or some part of the length, right? So it is simplified from continuum, but not that simplified like the concentrated plasticity. So in accuracy they are more accurate in some aspects from the lumped plasticity approach, but obviously the most accurate is the continuum approach, which is impractical for large scale applications for full buildings, right?